Problem set 4. So I am investigating a diffuse behavior of two necessary materials, X and Y. X is on the left, Y is on the right. So I'm going to go ahead and make this green. I'm going to make this X. I'm going to make this my Y. So, after long times at high temperatures, I see pores forming on the X side. So, I have pores forming on the X side. That means, again, let's think backwards about this problem. So, here, right here, let's say Y is right here, extra half planes. So that means that there's lots of vacancies kind of moving and gobbling up planes on the other side. So I know that my diffusivity of X is greater than my diffusivity of Y. So if that's the case, looking at the C frame, I know that my flux of X in the C frame is going to be greater than my flux of Y in the C frame. And I know by Kirkendall that I'm going to need to basically diffuse my flux of vacancies in the C frame must go in this direction. So what does that mean? So it means material, new material on this side is filling up these extra planes here. So this material is, we are expanding. And here, we're getting gobbled up. These vacancies are kind of gobbling up and destroying extra half planes. So we are expanding here, filling, we're destroying planes here, we are shrinking. And by shrinking and eating up those extra half planes, we can create the pores at long temperatures and actually high temperatures, excuse me, and long times. So that's essentially what we're going to be working with here. So, and that's going to be, so we answered actually quite a few questions already. So we've described this, we drew the fluxes, and actually, because this material is expanding, we know that the material here, the interface, is going to go in this direction. So this one's done. Flux, how we determined, and is this going to move? And okay, let's answer the rest of these problems. So what's the concentration profile for this diffusion couple? I like this problem. So if I were to draw the concentration as a function of X, so I know that because my diffusivity of X is higher, if I were to draw here, so it's 100% here, it's going to be non-zero on this side, whereas Y is going to be 100% here and then drop to 0. Because again, my diffusivity, this relationship here allows me to draw this. And then again, it'll change as a function of time. That's the initial at very, very small times. So which material is larger intrinsic diffusivity? We've already answered that one as well. Qualitatively and quantitative difference between intrinsic and self-diffusivity, that is described in the notes, and that was kind of in this discussion. Where is it? Conjugate forces. Where's our? All in this here. So in this page, we kind of talk about, again, chemical activity being different because, now we have this diffusion couple, and here's our kind of quantitative answer in equation 7. Additionally, if we want to kind of figure out the velocity of the interface, that's given to us by an equation 11. So let's go back to the problem set. So I believe that answers the rest of these values here, here, here. Great. So on to the next one. So now I'm interested in investigating how oxygen will diffuse into my ceramic mug. My mug is thick, so 50 millimeters thick. So let's go ahead and just say I have this circular mug, and you can kind of say it's very, very thick. Let's just say my mug is filled. So it is 50 millimeters. So basically, concentration of oxygen, which concentration of oxygen at atmospheric is about 0.21 or 21%, etc. So that's the conditions at x equals 0. And here at x equals 50, that's just kind of the end of my mug, so there's nothing there. So the diffusivity of oxygen is equal to 0.176 times 10 to the minus 4 meters squared per second. So we could actually go ahead and start to plug that into our Mathematica notebook. Don't save. I'm going to do, oops, that's not there. So let's go ahead and cancel this out. I'm going to create a new fresh notebook. And right here. And now I'm going to make sure I quit everything. So quit kernel local, etc., etc. So now I'm going to do, we can kind of look at the diffusivities. So D is equal to 0.176 times 10 to the minus 4. So now we need to, let's see, state any assumptions. So in terms of, we want to like plot essentially how the concentration profile is going to look as a function of time. So the PD I'm going to solve is dc dt equals d d squared c dx squared. The ODE I'm going to solve is using eta is equal to x over square root 4 dt. And my ODE that I'm going to solve, ODE, is going to be d squared dc d eta squared plus 2 eta dc eta equals 0. So that's my ODE. So my boundary conditions, or my assumption, is going to be, this is a pretty large distance, 50 millimeters here. So I'm going to assume I'm semi-infinite. So I'm going to assume that my concentration of oxygen at eta is equal to 0 at the surface is going to be equal to 0.21. My concentration of oxygen at eta is equal to infinity is going to be 0 because it's never going to diffuse that length. And so those are my boundary initial conditions. My assumption is semi-infinite. It'll be true as long as the length, which is equal to 50 millimeters, as long as the length is greater than 10 square root dt. And we could figure out what times my solution is valid by solving for that. So I'm going to solve when the length 50 times 10 to the minus 3, set it equal to 10 square root of d times t, solve for time, and I get 1.42 seconds, so it's not very long. So those are the points in time when my solution is valid, and my concentration profile is going to look like something like this. So concentration is a function of x, so initially it's going to be at this 0.2 value, so at small time it's going to be like this, and eventually it's going to go like this as time increases. So that's that problem in a nutshell. Now, germanium is an important material in semiconductor, band structures. We're going to dope it with extrinsic materials. Let's say that I want to dope GE with a layer of gold that penetrates 10 micrometers thick at 600 C. How long will this take? Penetration, what equation we're going to use? We're going to use our 2 square root dt, our engineering approximation. So x is equal to 10 micrometers. Diffusivity, we'll need to kind of look up that up. The temperature is equal, actually, it's at 600, so we have gold here. So what's the diffusivity of gold at 600? Looks to be about, let's just say it's 10 to the, let's just say it's 10 minus 10 centimeters squared per second, so that means 10 to the minus 14 meters squared per second. So that's my diffusivity, and now I can solve for time. So let's go ahead and do that. So 10 times 10, let's do solve, 10 times 10 to the minus 6, set it equal to 2 times square root of 10, or 1 times 10 to the minus 14 times time. Let's solve for how long it's going to take, 2,500 seconds. There we go. That's it. Calculate the activation energies of AU and AS. Ooh, this problem. We are going to have to, let's go ahead and zoom out a little bit. So I need AU and AS. So actually I already know basically the temperature here, AU, AS. So I'm going to say that this is about, again, so diffusivity of AU at 600 equals 10 to the 14 meters squared per second. Diffusivity of AS at 600 degrees C is equal to, let's see, it's 10 to the minus 13, so that means, let's see, 10 to the minus 13 meters squared per second, or actually centimeters squared per second. That would be 14, so then 10 to the minus 17, so 10 to the minus 17 meters squared per second, 17. Let's go ahead and kind of cross these out. Now I want to do a higher temperature, so let's do it 800. So for gold, diffusivity of AU at 800 degrees C, that's going to be equal to about 10 to the minus 13 meters squared per second. And then for AS, let's go ahead and look at it here. That's about 10 to the minus 11. So diffusivity of AS at 800 degrees C is going to be about, let's go ahead and let's look at this. So what is it? 10 to the minus 10 to the minus 11. So 10 to the minus 15 meters squared per second. I'm going to plug all those values in into my handy method. So dAU 800 equals 10 to the minus 1 times 10 to the minus 13. DAS 800 equals 1 times 10 to the minus 15. Let's go ahead and move it back over to the other side. So, oops, let's do a little bit more so I can see what material I'm looking at. DAU 600 equals 1 times 10 minus 14. DAS 600 equals 1 times 10 to the minus 17. All right, so those are my kind of values. I know my general equation for that. Oops, excuse me. Let me write that down. D equals D naught exponential minus QA divided by KT. I know what my K is, so let's go ahead. My K is equal to 1.38 times 10 to the minus 23. And now I could do solve. I need to do simultaneously that DAU 800, set that equal to D naught times exponential minus QA divided by K times 800 plus 273. Close it. And then also, I'm going to take the same expression, just going to change the temperature. So 600, and then that is going to be 600 here. And then I'm going to do close it, solve for D naught QA, and then I'm going to do for reals. There we go. What about for here? Let's bring this down. DAS, voila. So there we go. That's our values. So now we can go on to our kind of next and very important problems for our exam. So we're asked a couple of questions here. So one of them is, let's go ahead and draw. ZrO2 is critical in a number of nuclear applications, and it can be doped with Ta2O5. ZrO2 is known to form both cation-Frankel and Schottky defects. Activation energy for cation-Frankel is 1. Schottky defects is, so Schottky is going to be our dominant intrinsic reaction. We know our host is ZrO2. Our doping impurity is Ta2O5. Extrinsic reaction, blah, blah, blah. And then we also need to make sure concentration of ZR vacancies and how basically diffusivity of ZR. So we are looking for a plot like this. So log concentration VZR, which we know is 1, 2, 3, 4, ZrO2, over T. We know this is our intrinsic, extrinsic side. Same thing here. Log, and this is natural log of diffusivity of ZR, 1 divided by T. Intrinsic, extrinsic. So let's go ahead and write this out. So we know 1, that null goes to vacancy of ZR, 1, 2, 3, 4, plus vacancy in oxygen, 1, 2. So we need to know we have 2 of them. So that means our A sub S is equal to concentration vacancy ZR, 1, 2, 3, times concentration vacancy of oxygen squared equals exponential minus G formation Schottky over KT. We know that our electroneutrality expression is going to be basically 4 times vacancy ZR, 1, 2, 3, 4, equals 2 times, essentially, 2 times vacancy of oxygen here. So we use this expression to kind of plug that back in order to kind of solve. Again, we want the concentration of vacancy in oxygen, or actually the concentration of vacancy in ZR. So we're going to use this equation, and actually this expression, we're going to solve and plug this in for, right, this is a function of vacancy ZR. So we're going to be left with, once we plug in this, vacancy of oxygen is equal to 2 times this. So we're going to be left with an expression that's VZR 4 times VZR, actually 2 VZR, 3, 4 squared is equal to that. So we're going to get an expression where the concentration of vacancy ZR, 1, 2, 3, 4, scales as a function of exponential minus G formation of Schottky over 3 KT. So our concentration, or our slope, is going to be this minus G formation of Schottky over 3K. Again, because we do take the natural log, etc., etc. We know that the diffusivity of ZR is going to scale as T R squared F over 2D times also the vacancy concentration of ZR, 1, 2, 4. So we know that this hopping factor scales as exponential minus Gm divided by Kt. And we know the temperature relationship here. So for the intrinsic regime, our diffusivity is going to be minus Gm divided by K plus, or actually minus, G formation of Schottky over 3K. Now, for our extrinsic reaction, we know that our host is going to be this, Ta2O5 into ZrO2. So we know that we want to have the vacancy that we need, because again, we need to kind of look at the vacancies of zirconium. Vacancy Zr, 1, 2, 3, 4. So I also know that tantalum is this. So I'm going to do a tantalum replacing the Zr. That's going to give me a charge here. I need 4 of them. So now I need basically a 2 over here. I'm going to need 10 oxygens. I have charge neutrality, or mass and charge neutrality. So I'm good here. So 4 zirconium. Actually, I have 5 zirconium. And then done. So this extrinsic reaction does not vary as a function of temperature, so I just need my 4 vacancy Zr 4 equals Ta concentration. This is just my electroneutrality expression here. So I don't vary as a function of temperature for my concentration of zirconium vacancies. So really, all I have is the concentration here is just, this is just going to be the log of 1 over 4 times concentration Ta Zr here. So there's no slope here, doesn't vary as a function of temperature, but for the diffusivity, for the extrinsic, we still have this minus Gm by K. So we're going to have a very similar kind of answer here. So actually, I'm going to kind of erase. So sorry about that. Let's go ahead and get these up here. Let's erase these guys. Erase. And then let's go ahead and I'm going to also just kind of erase here. I want to try to keep this little plot. Keep this plot. Oh no! Let's go ahead and go back just a little bit. Erase here, erase here. All right. There we go. So I'm going to keep that plot, and then let's go ahead and read this problem now. Niobium, my host, is doped with impurity MgO. Frankel and Schottky defects. Frankel is this. Activation at Schottky is lower, so that's going to be my dominant reaction here. I need the concentration of oxygen vacancies and the diffusivity of oxygen. So I need to now plot the log of vacancies in oxygen, which is 1, 2, here and here. So 2, and then have the diffusivity of oxygen, the log. So that's the key part of this problem. So let's go ahead and draw those intrinsic reactions. So null, my host is going to be my vacancies in niobium, and B, which is going to be this minus 3, 4, 5 plus vacancies in oxygen, 1, 2. So I need 2 of these, I need 5 of these. So now my Ks is equal to vacancies in niobium, 1, 2, 3, 4, 5 squared times vacancies in oxygen times, or actually to the 5th power, which is going to be equal to exponential minus G formation shock Kt. So what's my natural electroneutrality expression? So vacancies niobium, 1, 2, 3, 4, 5. 5 is equal to 2 times vacancies of oxygen, and you can kind of see where we're going here. So my concentration vacancies of oxygen is going to scale as exponential minus G formation of Schottky over 7 Kt. So my slope here on this side is going to be minus G formation of Schottky over 7K. Here, this is going to be the same thing here, minus G formation of Schottky over 7K minus Gm over K. So just like last time for the migration energy. And then we're going to write our extrinsic reaction. So again, I know that my MgO is going into my Nb2O5. I need vacancies of oxygen. And then when I do my, I do this, Mg replacing Nb, so I'm going from 5 plus to 2 plus, so it's going to be minus 3. So I could do this 3 here, 2 here. So now I have 2 MgO. I need plus 2 oxygen, oxygen X. How many niobiums? I have 3 oxygens, I have 2 niobiums, and I have 2 more oxygens. I'm done. What's my electroneutrality expression? Well, it's going to be 2 times vacancy of oxygen equals 3 times Mg and B, 1, 2, 3. So now I could do that the vacancy of oxygen is flat, but that this value of the slope here is going to be log of 3 over 2 Mg and B, 2, 3, not 4, 3. And this is just going to have a slope of minus Gm divided by K. That's it. That's problem set 4 in a nutshell. So hopefully this is helpful as you kind of review for your exam, and I'll see you at the review session. Thanks.